else to call it except stuff. And it's to do with the last part in 16.2. Line integrals are a big thing in Calc 4. They're a big thing in engineering. One of the reasons they are a big thing is because this particular kind of line integral will actually calculate the work done on an object moving through a vector field F. So can you imagine this is my vector field F? So any given point x, y, right, there's a vector associated with it in 2D. And can you imagine that at this point here, t equals a in your space curve, and then your space curve does its thing and it ends up here at t equals b, and this fella here is your space curve. So the work done on an object starting here and traveling along this red line and finishing here is given by this line integral f dr. What we do to calculate it, however, is convert everything into t's, and that's what this is trying to represent. This represents t equals a to t equals b. This differential dr, where r is a space curve, is converted into r dashed of t, which is also a vector, dt, and f, the original vector field, f of xy, essentially gets turned into a function of t as well. And so what you'll have is a function of t, a vector function of t, dot product, a vector function of t. So when you do a dot product, you get a scalar. So that'll just be a function of t, dt. And that's essentially how to calculate work done. So you're going to be given a question or questions where you're told f, you're told the space curve, and your job is to find the work done in your space curve traveling through that vector field. It's like we lost Travis. There we go. So let's get the numbers right. I've rearranged the order so everything was together. So this is going to be questions 11 to question 16 now. Well, let's start with a version of 11. In question 11, the vector field is sine x cosine y and xz. So that's a three-dimensional vector field. And the space curve that's traveling through this vector field is a t cubed, a negative t cubed, at least in my example, a t, and it's going to go from t equals 0 to 1. So that's essentially the information, and you're being asked to find the work done. So you're being asked to find that guy. Okay, we got a whole load of things to fix here. It's going to be from 0 to 1. That's the easy bit. The vector f, which is this guy, this guy, this guy, is going to get converted into this guy, this guy, and this guy, but not with x, y's, and z anymore, but with t's. And we're going to use that for the x, this is going to be the y, and this is going to be the z. So instead of the sine of x, I'm going to get the sine of t cubed. Instead of the cosine of y, I'm going to get the cosine of negative t cubed. And instead of xz, I'm going to get x and z, so these two, and that's going to get me t to the 4. Are you comfortable with the vector field f being replaced in terms of t? Are we good with that? Now, dot product, r dashed of t. So what's that going to be? 3t squared, negative 3t squared, 1. and finish with a dt. So it's going to be the integral from 0 to 1. This vector dot product this guy dt. So dot product x's times x's. So that's going to get me 3t squared sine of t cubed. This guy times this guy is going to get me negative 3t squared cosine of negative t cubed. And this guy times this guy is going to get me t to the 4. Do you see that what we're now have in front of us is a calc to single integral in terms of the variable t? You agree it's just one big ugly integral.
Where did t from the fourth come from in the first work equation?
Hopefully it came from x and z, so t cubed times t.
Oh, okay.
Now, the practical part. You wouldn't want to do this in one go. It's just got too many things going on. So it's not that uncommon that if you've got a difficult integral with lots of moving parts, that you basically just split it into 3 separate integrals. So you'll get this answer, take away that answer. I just pulled out negative because I felt like it. And this answer. And once you've got those 3, you combine them, and that will be your final answer. Now, since this isn't a Calc 2 class, I don't want to spend too much time getting caught up on the weeds, but let's talk about how you would integrate this fella. What method would you use to integrate 3t squared sine of t cubed dt?
U subs?
So u sub in this case. And what would the u sub be?
T to the third.
Right, so I believe, don't quote me on this, but I believe you get sine u. Right. And that's easy to integrate. And this guy here is virtually the same. I think you'll probably end up, if you get a negative in another, you'll probably end up with a cosine u. And this is just power rule. Now, different world, right? Different question. Suppose it was 3t squared sine t, right? That might have happened. 3t squared sine t. Looks very similar, but not a u sub. What would be the technique you'd use for that situation?
Integration by parts.
Right. So always be on the lookout. If you see two things multiply together as we have here, your most likely go-to techniques are going to be u sub and integration by parts. And it's not like they're interchangeable, right? In some situations, you have to do the u sub. In the other situations, you have to do the integration by parts, right? And so, you know, that's part of the process. If you don't get that right, then the question's not going to be correct. Right, before I leave this question, because it is a bit messy the way I've written it, but have you got the gist of the process? You're going to have a space curve. You're going to have a vector field, then you have a space curve. All the x, y's, and z's get replaced by these fellas. So that means that your vector field will now be a vector with t's in it. Your r guy gets differentiated. Here, r guy gets differentiated. You stick a dt. So now you'll have your vector field in terms of t, r dashed of t in terms of t, dot product will give you a single integral, and then split it into bits to make it easy to calculate. And that's pretty much how most of the questions today are going to pan out. Ready to do another one? Any questions? Okay, let's go. Change pens, if you like, changing a pen. Nothing interesting in there. Okay. This is version A, question 13. Your vector field this time is only a 2D vector field. Looks like that. Your space curve doesn't exist. but it has to exist. So we have an extra problem here. If you tell me R of t, life is so much easier because then it's derivative dt, done. However, if you tell me the curve and you tell me it, in this case, as an x squared plus y squared equals 121, so I'm pretty sure I know what that is, isn't it? A circle radius 11. Then I'm going to be doing this fella, right? That's going to be my curve, which means I have to figure out how to parametricize it. Okay, it's a circle. Its radius is 11. If you are a circle or a piece of a circle, isn't there a polar version that you can use? We did one yesterday. So what's this x going to be called? 11 what?
Cosine t.
And then sine t. So if you ever get a circle or a part of a circle, use this, right, as your go-to guy. It's essentially r cos theta and r sine theta, right? Now, this is a complete circle. Since it's a complete circle, won't we be using that as our range? Was it yesterday they done one where it was the right-hand side of the circle?
Yeah.
Right, so when it's a right or the top half or whatever half it is, don't you just tweak the start and finish value of t and that'll take care of it? So if it had been the right-hand side, wouldn't we do negative pi to pi? And if it'd been the top, what, 0 to pi and so on and so forth. Are you comfortable with that now? Right. So we want to find the work done, which is this fella. And that's going to be the integral from 0 to 2 pi. Done. Now the vector f is x squared xy. X squared is going to be this guy squared, 121 cos squared t. Xy is going to be this guy times this guy, which is 121 sine t cosine t. So this here is essentially our vector field, right? Dot product with, well, you know this guy here, if you write it down in the format that you would if it was a space curve, wouldn't it be rewritten like this? So differentiate this fella, you get negative 11 sine t. Differentiate this guy, you get 11 cosine t dt. So this piece here is essentially r dashed of t, and then your little dt. So there's all the pieces. So the work done is going to be the integral from 0 to 2 pi dot product. This guy times this plus this guy times this. So let's see what we got. Oh, God in Hamel. Oh, I should have just called it 11 squared. So let's pretend it's 11 squared. So what am I going to get? I'm going to get negative 11 cubed cos squared t times sine t plus 11 cubed sine t cos squared t dt. Check that out. That times that is basically what 11 cubed is. There's a negative, got it. Cos squared, got it. Sine, got it. Okay.
Does that just go to 0?
Yeah, doesn't that count?
That is interesting. It does.
Your work is 0.
Oh,
Cool.
this would make sense because in physics, if you
It doesn't make sense. So before Lindsay does her thing, that does not make sense to the rest of us. Go for it, Lindsay.
it's like a physics thing. If you end on the same point you started, it's considered as no work being done.
Oh, it
So
does make sense.
Which is like, yeah, it's a weird thing, but you never actually move from your starting position. So yeah, no work is done.
Yes, we use a term later on called a conservative field. And if a field is a conservative field, it's a special property that vector fields have, then what you said is exactly true. There are some vector fields out there where that is not true. But it's like continuous functions. The vast majority of vector fields are conservative. And so what Lindsay said would happen. And in fact, the ones that we tend to concentrate on are conservative vector fields. That's kind of cool that math and physics met there for a minute. Right, the math said it was 0 and the physics said it makes sense that it should be 0. A surprise. Well, for me it was. I like surprises. Okay, next one is a boring trig. I'm not doing that one. Now the next one's at least got powers in it, so it's a little different. Oh, rewind. You know this guy here is x squared plus y squared is 121. Can you imagine that they went and said it travelled on that curve from x equals 1 to x equals 3? So imagine that had been your space curve, right? Now we need to convert this fellow into an R of t. Now we know what you do with circles, right? We've shown you the 11 cos 11 sine, but let's focus on this fella because he is kind of interesting. Okay, how would we parametricize the parabola y equals 4x squared? How would we get t involved? Don't overthink it. It's actually quite straightforward.
Just make it x equals t.
Now, from t equals where to t equals where? Well, from where x started to where x finished. That's where t will start and that's where t will finish. So most functions, you know, y equals 4x cubed minus 22x, parametricize very, very easily, don't they? You just make x equal t and y equal the formula. And the start and finish values of t will be the start and finish values of x. That makes sense?
Isn't that only for linear equations though?
Brooke, I didn't quite catch what you said. Could you say it again, please?
Isn't that only for linear equations? Oh, isn't that
You-
only for linear equations?
What this is, it's true for linear, but it's also true for any of them. So it's even bigger than just linear. It's true for everything.
Okay.
Which is nice because it means you don't need to learn different techniques for different shapes. And
Okay.
the exception, well, I wouldn't call it the exception to the rule, but the special case is circles. Don't circles, right, come out a little bit differently. They come out as cosines and sines. But technically speaking, now that I've thought about that, I would never do this because I don't think it would be nice math, but I could do this. If I rearranged this, at least the top half of the circle, wouldn't it be that fella? And so I could make x equal t and y equal that guy. And that would get me the top half of the circle. And then I'd have to do x equal t and y the 9-ish guy. I'd have to do that for the bottom half. I guess I could do that. Couldn't I just split my integral into 2 pieces? You know, do top half, bottom half, whatever. And that would give me a circle. Can you see why I wouldn't use that? Can you imagine how ugly that would be if it was being used inside an integral? I mean, square roots do not play well with integrals. Whereas trig tends to work much nicer. So I wouldn't say that's an exception. I think that's just a special case. But most functions just make x equals t, and y will be the same function, but in t. That was kind of cool. Oh, I was now about to do a power one, pretty boring, nothing really interesting going on, but for completeness sake, let's do 16. The vector field that we're going to deal with is x plus y, y take away z, and z cubed. And the space curve, it's back to being told who the space curve is. T squared, t cubed, t squared, and t goes from 0 to 1. I mean, the people who make these questions, you know, they could have a bit more imagination. I mean, t doesn't need to go from 0 to 1 all the time. I mean, they couldn't have said 2t cubed and 5t minus 7. You know, just mix and match it a little bit, but that's just me complaining. Okay, so the work done is going to be the line integral of f dot dr. In this case, it's going to be the integral from 0 to 1. Let's get all the pieces here. That's going to be my x, that's going to be my y, and that's going to be my z. So x add y is going to be t squared plus t cubed. Y take away z is going to be t cubed take away tz. And the last term is going to be z cubed, which is what, t to the 6. Dot product, derivative 2t, derivative 3t squared, derivative 2t, dt. As long as you tell me that, and that, isn't this quite mechanical? Isn't it just a process? You know, substitute, plug it in, substitute, plug it in. Right, okay, we've got a pretty messy dot product to do, but hopefully, well, who knows what will happen. This guy times this guy, that's going to be 2t times that guy, plus 3t squared times that guy. And looks like a 2t is the 7 to finish with. That times that is what? 2t cubed, 2t is a 4, 3t is a 5, take away 3t is a 4, plus 2t is a 7. Yeah, I thought so. It's pretty boring. Nothing interesting happening. Put the 7s first. Okay, they're taken care of. There's a 5 there, no more 5s, so I can go next. That's taken care of. And these kind of interact a little bit. Okay, now, can I just do my dot, dot, dot again? Isn't that just power rules? Just a big ugly add 1 to the power, divide by the new power. That's really what calculators are for, right? Now, we haven't done this. We only do 2 and 3 dimensional vector fields because for all practical purposes, at least if you live on the Earth and you use normal physics, aren't they the vector fields that you're likely to actually see in physical situations? But theoretically, couldn't I do a vector field in 4 dimensions? And a space curve in 4 dimensions? And therefore, theoretically at least, couldn't I find the work done in a 4th dimensional curve traveling through a 4th dimensional vector field? I have no idea in my even vaguest memories of what that could possibly be, but it exists mathematically. See how powerful we are? We can make things, we can do things in math, right? It's possible to do them in math. That might have no obvious meaning in reality. It's kind of cool. And then some bugger is going to come with a special theory of relativity that says, hey guys, you really do need to think of vector fields as 4 dimensions. Right. Some quirk will happen, you know, because of it. Yeah. Are we good? So, unless there's more questions, I'm going to call, stick a fork in it and call 16.2 done. Cool. Let's move on then. Here's 16.3. Which kind of comes to Lindsay's thing. Right. We're going to look at, right now I'm doing it in 2 dimensions because that's the easy way to calculate this, but you can do it with 3 or 4 dimensions as well. Here is a vector field. I'm going to call this guy P and this guy Q because that's what the textbook does and that's what some of the questions do. So, a vector field F made up of 2 pieces, a function of x and y, comma, a different function of x and y. If it has the property that the partial derivative of the first guy with respect to y is equal to the partial derivative of the second guy, but with respect to x, we call this vector field a conservative field. Think of conservative field as being nice field. Like, do you know, like continuous functions are nice, right? You can do good things with continuous functions. Don't all sorts of things that we like to do get screwed up if the function's got vertical asymptotes in it, right? Or get screwed up because there's a discontinuity, right? Think Calc 1. Do you really want to differentiate something at a discontinuity, like a jump discontinuity? No? Right. Well, we don't want to do line integrals with vector fields that aren't nice. And in our world, nice is conservative. For instance, one of the properties of a conservative field is that if you start at one point and you do a line integral and you finish at the same point that you started, that line integral will equal 0. In other words, the work will be 0, as Lindsay just told. So that's the first guy. Now, next piece of information. If you can find a function, right, a normal function, right, there's no arrow above it, it's a normal function. It's like f of xy is x squared minus y, right? It's got that shape to it. With the property that its gradient is your vector field function, then we have a conservative field. And I just remembered something. And this little fella has a special name. It's called a potential function. And I believe they borrowed the name potential, especially, from physics. Have any of you heard of potential functions in physics? Or at least the word potential?
Yes. It's called potential work, which there could be 0 work or there could be some work, and it could be positive or it could be negative depending on what they want us to find.
So the word potential, it sounds to me like we're using it in the same sense, but we're using it to give this thing here a name, right? So this little function, little f of xy, has a property that its gradient is the vector function, right? The vector field function. And we call them potential functions. Now, if you put that package together, here is a wonderful thing. And it's called the fundamental theorem of line integrals. And it says, if big capital F of xy is a conservative field, then the line integral, whoops, I've got my little arrow. You know those guys that we've been calculating for the last half hour or so? The line integral, right, the work done, this line integral is just the value of the potential function at the destination, take away the value of the potential function at the start. And it is independent of the path. What does that mean? Well, can you imagine? There's my guy again, right? Can you imagine your vector field, right? And your function starts here, right? And it curves to here. And you want to know the work done in getting from here to here. If the vector field is a conservative field, what it says is that you only need to find the value of the potential function at the start and the value of the potential function at the end. And if you take the value at the end and you take away the value at the start, that's your integral, that's your work done. Now, can you imagine how much work that's going to remove from the process? Right, I won't need to do dot products. In fact, I won't even need to do R dashed of t. I won't need to do quotient rules or integration by parts or any of those things. I won't actually integrate even. All I will do is I will find this potential function f. And if I can find them, I will find the value at here, right? And the value at here. Now, what that means, it means lots of things. One of the other really surprising things, except Lindsay and Brooke and everyone else are going to say it's not so surprising, is that it doesn't matter how you get to the start and finish. The work done is the same. And in this special world, the R of t that we use is irrelevant. All that's important is the potential function, and the potential function is connected to the vector function, right? The vector field. It's not connected to any of the R of t's. So they almost like leave the building. The only thing that's important is what's the XY coordinate of here, right? And what's the XY coordinate of here? That's the only part that R of t really takes place. To me, that is amazing. That some clever guy, and I use the word guy as generic for male or female, some clever guy figured that out. I wish I had that kind of brain. It's just amazing. So a lot of the stuff that we've been doing is now going to turn into a different job. Our goal, it's not an easy goal, but once you do it, it's really helpful, is to find the potential function. In fact, once we found the potential function, can't we do curves from anywhere to anywhere else without really doing anything extra? No. And as a side note, does anybody remember that?
Is that the fundamental theorem of calculus?
It is. Do you know that's just a special case of this thing? Okay, the notation's a bit backwards. That capital F is actually your potential function. We call it, in Calc 2, the antiderivative function. So it was staring us in the face, but it took a genius, whoever it is, hats off to them, to figure out how you could use it in the line integral context. So I'm going to focus today, for what time we've got left, in testing to see if a function is conservative. And if it is, we'll find the potential function. And if it is not conservative, question is over. Because if it's not a conservative function, that's why we had to learn all of 16.1 or 16.2, right? The previous section, right? Find line integrals, the f dot r dash t dt method, right? So that method has its uses. Its real use is when things are not conservative fields. You have to do it that way. So here goes. If you hold on with it for a second, where the heck am I? Close that one off. Go in. Stay signed in. View. Okay, so this is ozone 16.3. What one? Oh, start right at the start. Here's your guy. Little 2D fella. X, Y, plus Y to the 4. X to the 5 plus, 4xy. Okay, let's find out if it is conservative. Well, here's your test. Oh, I'm not quite sure what you're looking at. Okay, you were looking at the white screen, weren't you? Yeah. Okay, so here's our function. If you want to check for conservativeness, if there is such a word, you find this guy and you find out if he's equal to this guy. And he's P, he's Q. The partial derivative of this fella with respect to y is x plus 3y cubed. And the partial derivative of this guy with respect to x is 4x to the 4 plus 4y. So the answer...
Wouldn't it be 4y cubed, not 3y cubed?
Thank you. And it's not conservative. So that's pretty much the end of that question then. You know, if I keep going, I'll get one that does work. This is version 3. Again, it's still two-dimensional, which is pretty typical. It's y e to the x plus a sine of y, and it's an e. This one is much more promising. It's e to the x plus x cosine y. Okay, that's P, that's Q. Let's find out what the partial derivative of P is with respect to y. Well, that gets you e to the x, and that gets you plus cosine y. And let's do Q now with respect to x, and that's also e to the x, and that's also cosine y. So we have a conservative field. Are you comfortable about the test? How you find out if a vector field is conservative, in this case it is, or not, in this case it's not, right? And it's a good idea to do this test before you move on to finding the potential function, right, the little f. Because if it's not conservative, you shouldn't bother. One, you probably won't be able to find a conservative field, a potential function. And even if by fluke of numbers you did find one, it wouldn't work. In other words, it couldn't be used. So let's find the fella. So I'm just rewriting the equation down again because I want plenty of room. Which is fine. And what do we know about the potential function? Well, we're going to find a little function that has the property that its gradient It's him. Okay. So what do we know about this Scylla? Well, if I asked you to find the gradient of this, wouldn't you call it df by dx and df by dy? Would you agree? Remember the gradient? And now if I match this with that, what I now have is that the partial derivative with respect to x of the potential function should equal this guy, which I'm going to call equation 1. And the second one should be equal to that guy, which I'm going to call equation 2. And we are going to find who f is. Now, I know these are partial derivatives, but pretend for a minute they were just derivatives. If I said to you, dy by dx is x cubed, how would you find y? What process would you do if I tell you what dy by dx is? What process would you do to get y? It's not a trick question. And if I told you, you'd all say yes. But if you figure it out yourself, it will stick in better.
Wouldn't you just
Power
integrate?
rule?
You just integrate. Find the antiderivative. So we're going to find the antiderivative with respect to x. Now, y e to the x, won't that just give you y e to the x? Like 5e to the x as an integral 5e to the x. So far, so good. Now, be careful. What do you get if you integrate with respect to x? Integrate with respect to x, the sine of y.
X sine y.
Agreed. Now, typically in math, don't you say plus c? Agreed? We tweak it a little bit, and it's not plus c, but plus an unknown function of y. Because if it's an unknown function of y, when you differentiate it with respect to x, won't it disappear? And we're halfway there. Now let's do it with the second one. If you take this guy and you integrate him with respect to y, what will e to the x get you? E to the x, what will it get you if you find its antiderivative with respect to y?
e to the xy?
Yes. It's just like 5 gets you 5y. Now, whoops. That's okay. What will you get from this fella? X cosine y when you integrate it with respect to y.
X sine y.
And instead of a plus c, you have a plus some function, we'll call it h of x. Now, what you will do is you will look at both of these answers and you will merge them together. Well, in this case, the merging is quite easy. You get that? Are you comfortable that the potential function little f is this guy? Because
If we're merging, shouldn't there be a 2 out in front because they're the same?
oh no, merging, I'm not meaning adding. Merging, I'm just saying looking at both and seeing what single function of f would be able to represent both situations. So it's not adding. I don't mean it in that sense.
Okay, so
F
you're
is
just
this
looking
guy.
to see what is the same to get your function of f?
Right. Now, these two little weird plus gy and plus hx didn't come into the the question. But can you imagine in a different world where there might have been a plus 2x here and maybe a little minus 3y there? Whatever it was, right? Can you imagine that happening? Now, when I merge them, do you see that this guy and this guy would get merged with my answer? This fella allows the 2x to happen, and this fella allows the 3y to happen. So when you are merging them, you're basically putting them together, and the guys they share, you keep. And if a guy has something that the other guy doesn't, it goes in the mix as well. And the g of y and h of x.
Just not their values of c, which is the g of y and h of x.
Yes.
Okay.
So the g of y is just a placeholder if there's any y's left over somewhere. And the h of x is a placeholder if there are any x's left over, right? So it's the way that we cover our butts. Surprisingly enough, these things very rarely happen. And these two guys end up being the same more often than not. Right, so more often than not, this guy is these two guys, right? But it can happen. Now that I've got that potential function, can you imagine that we had this fella here? Right? And they gave us an r of t, and I'm just going overboard because I want to. And it was t cubed e to the t sine t over t plus 1, and it was t squared cosine t. Can you imagine the space curve was really ugly? Like that. If I have the potential function, I don't care how ugly that is. Don't I just need to know where does the point start and where does it finish? And so can we pretend that it started at the point 0, 1, right? That'll be x and y. And it finished at the point 1, 2. And according to what we have here then, the line integral of f dr would just be the value of the function at the end point, take away the value of the potential function at the start. And you see that is so much easier to calculate, isn't it? Can you imagine how ugly that would look as an r dashed of t? And then you join it with this guy. Can you imagine that the integral would be so ridiculously ugly you probably couldn't do it? But if I can find its potential function, let's get these guys out of the way because they're distracting me now. Then all I need to know is, where does this space curve start, right? At t equals 1, what's the x and y coordinate? Where does this space curve finish, right? At t equals 10, what's the x and y coordinate, right? That's what these would be. And then end, takeaway, start, you're done. Does that make sense?
Yeah, it's pretty nifty.
It is cool. Now, remember that thing about the closed loop? And the answer is always 0 if it's a conservative field, right? Like the circle one. But it doesn't need to be a circle. Couldn't it be some, ziggy thing? Well, in that world, won't your start position be the same place as your finish position? Therefore, your answer is always going to be 0.
Yes.
Isn't that cool?
That is very cool. It just, because they just had me go through engineering physics a while back here. It's just, I'm seeing the relations, a lot of relations between it.
Right, when you do engineering physics, not everybody here is ever going to do it, but when you did it, did they talk about potential functions? Or what I'm doing here is, wow, I wish they told me that.
So kind of, it did talk about potential functions, but we didn't, it's more calculus based rather than higher calculus. Like it's like a calc 2, calc 1 based type thing.
Okay.
And if I would have known this, it would have made everything a whole lot easier.
Yeah, sometimes I get a feeling the people in physics and chemistry, but it's not our fault. It's their fault because we're right and they're wrong. You can't really do this math with a Calc 2 student. right? You just can't. Can you imagine me doing Calc 4
Correct.
stuff with you while you were in Calc 2? Anna,
That'd be-
would you just run out the room screaming, right? Right. Your mathematical knowledge and maturity needs to develop. And so we can't really show you this stuff until, and you're God, I
Yeah,
wish it was-
but that's why engineering physics, they don't introduce these equations. They give you a different type of equation to find work and everything. But if I would have known this, I could have looked at the equation and gone, oh, that would have been easier to know that those were my limits.
Right. You could almost, if you have your notes, go back and look at a question and see how it would have worked with this situation.
Yeah, and I kind of am doing that because I help newer engineers going through the program as tutoring. So I
Mhm.
still have my old notes, and I was looking at that the other day, helping out a student. I was just like, oh my goodness, here's the correlation. This is where they meet up again between math and physics.
So yeah, I was going to say, you lot of, if you do more math, I don't know how much more math you're going to do, but there is a phenomenal amount of really cool stuff that you haven't met
Yeah.
yet. And you are, if you do a lot of math, you are going to
I
get
love
some
math.
blow your head stuff. So have fun being an engineer, but you are really cool stuff in the future. And I'm not going to waste someone else's joy of showing you some stuff.
Well, I plan on taking as many math classes and other classes I can after going through the engineering program for them.
Just for fun and giggles.
Just for fun and giggle.
That's cool. Okay, God, the time. I apologize profusely. I was having so much fun, I forgot what time was. Okay, say hi, everybody. I shall see you all tomorrow.